Okay, so on homework 12, please do your own homework. It's important that you know how to do these problems. This section is going to be a lot easier than the combustion equations, but both will be on the final, so please make sure you know how to do that. It's due next Thursday, so 1 week from today. And please go fill out your course evaluations. Those are due by, I think, the time of the final or last day of class. I'm not sure exactly when the due date is on that, but go ahead and get those started, get them done. And then hopefully you're working on preparing for the final. You could be making your equation sheets early, just kind of get those in there and make sure that you fully understand how to do some of the problems that we've done in the last section, and then of course remembering back to previous sections the work that we've done on that. So today we're moving on to wind energy. So this is a continuation of the topic of renewable energy, and we're focusing primarily on energy that comes from the wind today. Last week, or on Tuesday, was solar. And then, yes, question?
For the final, will I have 2 sheets?
I'll give you 3 sheets.
Okay, and then
Can we trade a sheet for the points on it?
the final, is it cumulative or is it just the newer stuff?
It is cumulative, but the emphasis will be on what we've learned since the last exam.
Okay.
It has to be cumulative because it all builds on itself, but yeah. And I'll talk in more detail about the final next week, on Thursday. So we'll have class next Thursday, that will be the review day, and then it's 1 week from that day until your final, so you have time to practice and prepare and study. Okay, so again, just to re-emphasize this whole idea of renewable energy is important to us because as we continue to use fossil fuels, 2 things are happening. 1, those fuel sources are being depleted. They're not renewable. It takes millions of years for coal and oil and natural gas to be formed. And we're continuing to pollute the environment. So at every step of the process, whether it be obtaining those fuel sources from the ground causes environmental pollution, burning those fuel sources also causes pollution. So they're very dirty sources of fuel. There is no such thing as clean coal, despite that moniker that's often used in the news and headlines. It's not a clean process by any means, both for those who are working in the mines and those who are breathing the air near coal power plants. So we need to look at using more renewables, so that can help offset the amount of fossil fuels that we consume. But we also really need to focus on utilizing the resources that we have in more effective ways. So we need to work on energy conservation in our own homes. And by conservation of energy, we don't mean the mass balance and the energy balance. We're talking about using less. So turn off your lights if it's broad daylight outside. Don't have a TV blaring if you're not in the room. Turn off the fans. Try to be more aware of the ways that you use energy. And there are a lot of tools online, as well as AEP has representatives that can come to your home and they can analyze your energy usage and give you ideas of where you can save. So that's beneficial not only to your pocketbook, but then also to the environment to have those energy savings implemented. So when we're talking about renewable energy, again, renewable energy refers to energy that comes from a source that isn't depleted with use. So we're not depleting the energy from the sun in any noticeable way. We're not depleting the energy from wind in any noticeable way, as we talk about that today. So the wind has been used as a source of energy since ancient times. So the first kind of record that we see of the wind being used is in ancient Egyptian times, where they actually used the wind to create sailboats. And working today. Hold on. Last time. There we go. All right. I like using this pen. Okay, so if we look at ancient Egyptian times, even hieroglyphs, they have a record of using the wind to propel ships across the ocean. In the Islamic world as well, there has been a lot of evidence of the wind being used to actually pump water or to grind grain. They weren't generating electricity with these windmills, they were using them for agricultural purposes or for production of food. We see a lot of windmills in Amsterdam, in Holland, in the Netherlands, that was quite common in the northern European areas. The wind was used to create music. They recognized that if they can hang chimes or bells, that the wind would be able to create somewhat mystical sounds, and there were a lot of religious implications around the creation of music via the wind, particularly in Buddhist or Hindu traditions. This is kind of an interesting structure. This is from Iran, and it's a cooling tower that somehow the way that the wind blows through this, it's able to form ice on the inside of this tower, depending on outside temperatures. So they would use this both to create ice in cooler months, and then they would use this tower to store ice or use it like a refrigerator in the warmer months so that they could have cooling capacities. And then, of course, the wind was also used for enjoyment, for flying kites and seeing things drift through the air. So the wind has been around since the beginning of time, and it's been used by man for our own purposes and our own benefits for thousands and thousands of years. In the U.S. alone, there are over 6 million small windmills in operation. And we make the distinction between a windmill and a wind turbine. A wind turbine is used specifically to generate electricity. A windmill is used for mechanical purposes. So windmills can be used to pump water, they can be used to grind grain, they can be used to saw logs, but when we talk about the windmills in the U.S., there's over 6 million of them, just small-scale windmills. And they were used to generate electricity as early as the early 1900s. Some of those windmills were put into production, connected to generators, and then used to generate electricity. And in the 1970s, there was a huge energy crisis. There were fuel shortages where we started really looking at alternative sources. I think in the 70s a panic arose where in the United States at least we felt like we needed to completely eliminate our dependence on fossil fuels. Well, then in the 80s there was a resurgence of fuel imports and fuel production within the U.S., so we kind of gave up on some of those ideas that we had. But modern wind turbines started to come into effect in the 1970s. And a lot of what we're going to do and look at and analyze today has to do with modern wind turbines. And when we look at West Virginia specifically, there's about 700 megawatts of power generation that comes from wind turbines within our state, which is less than 2% of the total energy generation for our state. Where's the link? I guess we'll put it here. Okay. So let's talk about West Virginia specifically. Similar to the map that we saw with solar radiation, or incident solar radiation, this is a map of average wind speeds in the U.S. And you can see that areas that have this purplish color or even a bluish color in some parts of Wyoming have very high wind speeds compared to some of the other parts of the U.S. So on this scale, this is 10.5 is the max and 4.0 is the minimum. Where do we fall in West Virginia? Pretty close to the bottom, right? So we're kind of around here, 4.5 to 5 meters per second, with the exception of, you can kind of see this band through the state where there is higher wind flowing through, and that has to do with the regions between two of these mountain slopes where we can obtain higher wind production, or we notice that there are higher winds. So if you look at this map and you compare it to where the current wind power generation plants or wind farms are located within the U.S., you can see that they're predominantly located in areas where there is a significant amount of wind, that it makes more sense for them to be in those locations. And if we look up close at the map of West Virginia, we can see that this band of higher wind, that's where most of the plants are located. So in West Virginia, and then moving up into Virginia, Pennsylvania, in those areas. And then one little solitary wind farm over here, this is in Greenbrier County. So the majority of our wind production is in the northeast, in the Potomac Highlands, and there's not much in other parts of the state. And so we consider wind power to be free, but the wind isn't always blowing, and it's not always blowing hard or fast or quickly, however you want to designate it, everywhere. Okay, so we can use it and we can obtain it, we can get it, but there's no guarantee that we're always going to have wind. And then traditional large turbines, and we'll see the scale of some of these turbines, they're huge. They require either mountaintops or large open spaces, that you can't just put one of these gigantic turbines anywhere. And by many people, they're viewed as unsightly, noisy, and they obstruct the view. So if we're putting them in these wide open natural places and somebody has property adjacent to it, there may be complaints or there may be petitions by landowners to prevent wind farms from going in. So that's a barrier to entry. And bird strikes are not uncommon. So it's estimated that it's around 300,000 birds per year that are killed by wind turbines from these wind farms. So let's look at some of these challenges and let's see if we can address some of the concerns and possibly find workarounds for them. And these are not my unique ideas. These are things that are already being implemented. So one idea is to go offshore because the temperature differential between the land and the sea is usually such that there's always wind blowing off the ocean, either off from the land to the sea or from the sea to the land, depending on which is warmer at night or during the daytime. So there are wind farms that are put off coast. So these giant wind turbines are buoyed. They're not actually planted into the ground. They're floating on buoys, but they're tethered so that they can't float away. They're also able to spin on their axis so that depending on the direction of the wind flow, they can always have wind in their sails, so to speak, or at their blades. And there's several different mechanisms for buoying those. Another of these arrays of floating wind farms, which are not quite as common, and this I think is probably just a rendering of an idea. It's not necessarily a wind farm that's in production. Okay, another solution is to go higher because there's a significant increase in wind speed with altitude. So as you go higher up into the atmosphere, the conditions change, the wind is blowing faster, it's blowing harder. And so there are several companies that are really investing a lot of time into developing the technology so that they can have wind farms that are up 300 meters or higher. So in some cases it's similar to a kite, where it's just this floating turbine, where in some cases maybe it's filled with helium or a lighter substance so that it can float. In other cases it's just simply acting as a kite, so the wind is keeping it in place. There's also, this is one that's been developed by Google, where it's like an airfoil that once you get it up to a certain height, it can maintain its position like a kite, and then these turbines, these mini turbines, will spin and generate electricity. And then of course there's a tether attached to the ground so that the electricity can be transmitted back. So go higher, that's one potential solution, and it's much less expensive to have a tethered solution than trying to make these wind turbines infinitely taller. That those are already so huge that they cost quite a lot of money to create. Okay, so another solution is to integrate these wind farms into existing structures. This is a skyscraper in Bahrain, which is in the Middle East, and so they've implemented these turbines in between these two towers in order to have some electrical power generation in a building that's already built or already there. So they don't have to erect separate towers, they can just use the building facade or the structure as it's already there. And, you know, offset some of the costs of electrical consumption within the building itself. There are also some aesthetically pleasing or more pleasing turbine designs where they don't look maybe quite as ostentatious or ugly. It's just this big, ginormous, three-bladed thing. So these would be maybe for smaller scale applications that you could have just in your own home. So you could use it on an existing building.
What's the power difference between a home wind turbine and a solar panel?
So it really depends. Generally, you can get more power output out of a wind turbine for the same cost than you can for a solar panel. But it also depends on how windy of an area you live in versus how much sun you receive. So there are a lot of factors that go into establishing that cost. But like this wind turbine, these are on the order of maybe 1,000 watts, something like that, for just a single wind turbine. And the upkeep and maintenance is generally a lot lower than for solar panels too. So, but there are really a lot of variables that go into determining whether one is a better option for your home than another.
As we saw yesterday and today, the location we're in isn't particularly great for solar panels and isn't particularly great for wind turbines. So is one better than the other in this area?
I think they're about equivalent.
Okay.
Yeah. And it really also depends because you can be in one part of a holler. I run a lot along the trails in the woods, and there are areas that are always windy no matter what. And then there are areas where the air is always still and calm. So because we have such varying topography throughout our state, there will be places that will always be windy and places that will always be calm. So the places that are always calm are also generally the places that don't get a lot of sun because they're further down into the hollers. But it is something that is, it is a grave consideration for West Virginia that we're not ideally placed for significant gains in wind power or solar power, but we can offset some of the fossil fuel consumption if we're careful about our usage too. So,
okay.
Yeah, so it's an important point to consider. Okay, so then the last metric is that birds are killed by the turbines, and that's a lot of times that is used as the main complaint about these wind turbines. Is, well, they're not good for the environment. They're killing the wildlife, right? So they're killing all these birds. If we look at the statistics, the number of birds killed per year in the U.S. by cats is about 2.4 billion, and this is primarily like songbirds, smaller birds, by house cats, right? So wind turbines is much lower. It's about 234,000, and I don't know what's the deal with U.S. cats versus Canadian cats.
Sorry.
Nearly as many birds.
It's the same difference between those things are mean.
That's probably true. Maybe the birds are bigger in Canada.
People are nice, the birds
So, cats are the real enemy, not wind turbines. All right. So this takes us to a discussion of wind turbine design, and there's really many, many different ways to do it. Yes?
Is it more space efficient, or is it just cut down on power too much to like put wind turbines in the same place as a solar farm? Because the other main complaint about wind turbines is that they take up so much space.
Right. So that is not, it's not necessarily a problem to have wind turbines in the same space as a solar farm.
What material are most wind turbines made out of?
It's usually like steel and aluminum parts. And there's actually this video we'll watch in just a minute. It'll talk kind of about the design challenges in building these things because they're really, really big. When you see them way off in the distance, they don't look that big. They're just like all these cute little wind turbines spinning in the distance. If you're ever up close to one of those, or if you see one of the trucks that's carrying components or parts on the freeway, they're massive. I mean, the blade is as big as this room, the length of the room, a single blade. They're huge. So material costs are pretty significant with these wind turbines. So there's two primary categories that we place wind turbines in. There's the horizontal axis turbines and vertical axis turbines. So basically that means that the horizontal axis is what is spinning versus the vertical axis is what is spinning. And primarily the mechanism by which each of these works is this uses lift and this uses drag. And you don't have to know specifically what qualifies as a lift versus a drag, but it's important to know that the horizontal axis turbines by and large are more efficient than the vertical axis turbines. However, the vertical axis turbines are often used in applications where this large horizontal axis turbine would need significantly more space than one of these vertical axis. So when you look at small scale turbines, particularly when they're being implemented as kinetic art, it's often a vertical axis turbine. And this video, hopefully figure out how to make it. It's pretty interesting because it talks about the reasoning behind why most turbines in production...
People have been harnessing the power of the wind for thousands of years. The earliest recorded evidence of this can be seen over 1,000 years ago in Persia. But these machines have evolved from simple devices to crush grain and pump water to towering monsters generating enough electricity to power entire towns. Traditional wind turbines come in many shapes and designs, but they have all given way to a fairly consistent three-blade design. Today we're going to answer the question, why do wind turbines have three blades? We can imagine each blade as wrench, tightening, and knot. If we increase the length of the wrench, we can generate more torque. That's the force that causes rotation. Likewise, if we add a second wrench, we can apply even more force. The same principle applies to wind turbines. So naturally, you may think, why not add as many blades and make them as long as possible? The biggest wind turbine has a diameter of 164 meters. Each blade weighs 3 tons, and each costs hundreds of thousands of dollars to manufacture. So more blades equals more weight and more cost. So maybe less blades is better? Let's compare our standard 3-blade design to its immediate competitor, a 2-blade turbine and a 4-blade turbine. Let's assume they have the same blade design for now. We can easily eliminate the 4-blade design with a quick cost analysis. Each of these blades costs a lot of money. Adding a 4th blade provides such a marginal increase in performance that it does not justify the additional cost. So it's down to 2 and 3 blades. A 2-bladed design can match the performance of a 3-bladed design by increasing the chord of the blade by 50%, which eliminates the cost advantage, so it's pointless. Or we can increase the rotational speed by 22.5%. Turbines with 2 blades will spin faster in the same wind due to the reduced drag experience, but spinning faster is a negative. Let's explore why. A faster spinning blade will generate more noise. This is what a wind turbine sounds like up close. Yeah, people don't like living next to these things, so we need to minimize the noise they make by minimizing their speed. Next, we need to worry about centrifugal force. As the blades spin faster, their apparent weight increases. Thus, the central hub and the blades need to be stronger to resist the additional stress. Again, this adds cost. This is what can happen when a wind turbine brakes fail from strong winds. So a 3-blade design can generate more power at slower rotational speed than a 2-blade design, while being more cost efficient than a 4-bladed option. So the 3-bladed design is our Goldilocks choice, not too much and not too little. Thanks for watching and happy Earth Day. Don't forget to subscribe and see my next video, which will explain the history and physics behind windmills.
So that was a pretty interesting discussion about why they are 3-blade designs. So pretty much any wind turbine that you see in those big wind farms, they have a very similar airfoil and a 3-blade design because that process has already been optimized for cost. That somebody has gone through all of the analysis of how much material each turbine uses, what airfoil is the most efficient or effective at certain wind speeds, and then how many blades can optimize how much electricity is able to be generated and balancing that with the cost of producing and maintaining those blades. Okay, so the horizontal axis wind turbines are called HAWTs, HOTS, and the vertical axis wind turbines are VAWTs. That's just the abbreviation for that. And then anytime we have multiple turbines clustered together, we call it a wind farm. So we're farming wind. Similarly, solar farms are often, or solar panels clustered together are often called solar farms. And then, as was mentioned previously, the horizontal axis wind turbines are more efficient than the vertical axis, and that's what you predominantly will see in production. And each wind turbine will have a characteristic performance curve, which displays three main attributes. The first is the cut-in speed, so it's the maximum speed at which useful electricity is beginning to be generated. The rated speed, which is the wind speed that delivers the maximum amount of electricity or maximum power. And then the cutout speed is the speed at which the turbine is designed, the maximum wind speed at which the turbine is designed to produce power. And so the cutout speed is the wind speed at which the turbine, once it recognizes, because it's rotating at a certain rotations per minute and there's some mechanism in there that tells it what wind speed it's operating at, it puts on the brakes. For two reasons. One is that it's diminishing returns on actually producing any usable electricity because of the way the airfoil is designed. And also, as we saw in that video, that as they start rotating and spinning too fast, the centrifugal forces are incredible because those blades are so big and so heavy that they can actually destroy the turbine. And those things cost hundreds of thousands of dollars to build, so a catastrophic event like that is very costly. So there's a braking system that's built in, such that when we reach the cutout speed, the turbine goes into a shutdown mode where it turns off the blades so that it can't spin any further. So, yeah, but it's not, the maximum wind speed is not where you get the maximum power output. There's actually a curve, and that's just based on the airfoil design of the particular turbine. So this curve will be different for every turbine that has a different blade length, diameter, airfoil design, and height.
So the cutout speed is when it stops, right?
Yeah.
Okay.
So it puts on the brakes. There's some sort of a mechanism in there. It's like a safety switch that once it reaches that maximum velocity, it shuts the turbine off. And what I don't know fully is how it turns back on, how it measures. Maybe there's like a pitot, what's that called?
There's a
pitot tube or something. That's for directing it. But there's something so that it can measure the wind speed and then know when it's safe for it to turn back on.
Is it constantly generating power as long as it spins, or is there, okay.
Yeah, so even if the wind dies down because of the inertial forces, these will continue to spin for a while until they eventually wind down. They have low friction hubs and just the inertia from these blades. It will continue to spin even if there's zero wind, just as it's winding down. Do you have a question?
I know you had the video of when it reaches like its critical speed or whatever, but have you ever seen when the brakes fail?
That was when the brakes.
That was when they failed?
That's the brakes failed, yeah.
I know there's some when it becomes just like a big fireball, like 70
yeah,
miles
probably
an hour.
happens
So
too.
the
The
brakes
The one got struck by
yeah,
lightning and
fire.
caught on fire.
Yeah.
Yeah, so the cutout speed is a safety mechanism, and if for some reason those brakes fail and they don't turn off and that turbine continues to spin at higher and higher speeds, then you can have catastrophic failure. So there's a safety factor built in here, right? So it's not like right at the cutout speed is when it would explode. It's somewhere further along in velocity, but you do it such that you can turn the turbine off and be able to brake it, because again, as it starts moving faster and faster and faster, those inertial forces are so great that it would require a greater amount of braking power to turn it off. So the cutout speed, there's some value that's designated based on economic cost and possibility of failure for each turbine. Any other questions on this curve? All right, so when we talk about the wind power potential of a turbine, it varies with the velocity of the wind, or the average velocity of the wind in the particular location. So if there's an average velocity or velocity of the wind, the power available is equal to 1/2 times the mass flow rate times the velocity squared. So what does this look like to you? What kind of a term does that look like? Yeah, that's a kinetic energy term. So when we're determining the amount of power available to this wind turbine, it's predominantly just the kinetic energy forces of the wind. So as the wind passes over the blades, it slows down, and some of that energy is transferred to kinetic energy, so we'll look at that a little bit later too. We can also rewrite the mass flow rate of this air in terms of the density of the air and the velocity of the air. So if we substitute that into this equation, we can come up with an alternate expression where if we know the density of the air, we know the area of the blades, and the area is based on the diameter, so the circular area, pi d squared over 4, it's not the surface area of the blade, it's the circular area, times the velocity cubed. So you just need to know the size of your turbine, how fast the wind is blowing, and what the current air density is, which would vary based on the altitude, the location, the air temperature. So density is not necessarily a constant, but it is something that can be figured out and calculated. So if we assume that air is an ideal gas, another way to write this equation, simply in terms of property values which can be measured, is using the pressure and air temperature to put that into the equation so that we can calculate it based on those known quantities or known factors for any given location. So again, velocity has to be somehow measured, which is not that hard to do, and we would need to know the pressure and temperature of the air and the size of our wind turbine. And then we could calculate the maximum available power for that particular site, the wind power potential. Note that this is like exergy, similar to an exergy term, in that we're looking at how much is available, not necessarily how much we're going to get from our turbine. So let's do an example. Isn't that funny? So a wind turbine with blade diameter of 50 meters is to be installed in a location where the average wind velocity is 7.5 meters per second. The average temperature and pressure of ambient air in this location are 23 Celsius and 96 kilopascals respectively. Determine the wind power potential. Okay, so how do we go about finding that wind power potential given the variables that we have here? So W dot available is equal to what? Did we already forget?
Is 1/2 mass flow rate.
Okay, so we can start from there. 1/2 times the mass flow rate times what?
Velocity squared.
Velocity squared. Okay, so mass flow rate is equal to what? In terms of density and velocity? Rho VA. Okay, so we can sub that in 1/2 times rho A V cubed. Okay, what is density equal to in terms of other property values for the ideal gas law?
I have a question. When it says blade diameter, does that mean the width of each individual blade?
What's a diameter?
Or is it talking about how it's spinning?
Right. So it's this distance.
Oh,
Pressure over RT.
Okay, so density is equal to P over RT. All right? So we plug that back in. 1/2 times P A V cubed over RT. All right? And what's A? What's the area of the
Pi d
circle?
squared over 4.
Pi d squared over 4. So it would be pi over 8 times pressure times the diameter squared times v cubed over RT. Okay, so we can put in the numbers for that. So pi over 8 times the pressure, which is 96 kilopascals, times the diameter, which is 50 meters squared, times the velocity, which is 7.5 meters per second, divided by R. What's R for air? Close, 0.2870. Kilopascals times meters cubed per kilogram Kelvin. And the temperature, what is the temperature?
23 Celsius or
23 plus
296 Kelvin.
273 Kelvin. Okay, so we find that our W dot available is equal to 468,038.2 meters squared times kilogram per second cubed. Ugh, what are those units? What should they be? For
This-
power.
There's hot watts.
Okay, it should be watts. Okay, so we know from before that 1 kilojoule per kilogram is equal to 1,000 meters squared per second squared. And 1 kilowatt is equal to 1,000 meters squared kilogram per second cubed. So this is a unit of watts. So if we want to convert it to kilowatts, W dot available, we have to divide by 1,000. So it's 468 kilowatts. So this is an important relationship to remember, particularly as we're doing these problems, because you have to be very careful on units with these when you're dealing with kinetic energy and pressures, but the units don't always mesh well. Okay, any questions on this example? All right, so wind power density is just the available wind power divided by the area. So this is looking at the wind power density of an individual turbine. So you say, okay, how much wind power is available to me? And then if I divide through by my turbine area, then I can get this term called the wind power density. And this is what's often used to compare turbine farms or individual turbines one to another, is that we want a turbine with the highest wind power density possible. So it's just 1/2 times rho times v cubed, and if we're using the average velocity, then we just put this bar over the top of it to indicate that it's an average value. Because the wind isn't always blowing at 6 meters per second. One day it's 4, one day it's 8, one day it's 10, one day it's 5. So generally what they do is they look at a location over an entire year and find an average velocity for that year so that they can calculate their annual power production based on that year time. Okay. So, some general rules of thumb is that a location with a wind power density of less than 100 watts per meter squared is a poor site. Around 400 is a good site, and greater than 700 watts per meter squared would be a really great site. So we'd have to go back to our wind map and see what the average velocities are at a particular location, and then design a turbine with a certain diameter such that we can have a wind power density greater than 400 watts per meter squared. So that's a design problem, an optimization problem. And then in that, as we were doing that design, we would have to consider the costs involved of creating this turbine. Because if you're in an area where in order to get 400 watts per meter squared, you had to have some really, really huge turbine, then maybe it's not necessarily economically feasible to generate wind power in that area. So some other factors that might influence the selection would be if there's significant atmospheric turbulence. So if you're trying to set it up in a location or a place where the winds are quite strong, but they're also quite turbulent, that can be problematic for the blades. It can cause rotational torquing. It can cause additional vibrations that can damage the turbines or cause them to have a failure. And then if there are any obstructions, so you wouldn't want to set your turbine in a place where is common to plane traffic, or there are power lines, or obvious things like that. And then you also have to consider the land cost, because the cost of large pieces of land in order to put in a wind farm, if it's billions of dollars for this land in California, possibly that's not economically feasible to do that. So there have been wind farms that have been proposed, and they've been turned down also because the people in the surrounding areas have petitioned against them. If they don't want a wind farm in their backyard, either because of noise, or they view it as unsightly, or in many cases that they feel like it's an environmental problem for the native wildlife, which we see is less problematic than cats. Okay, cats are kind of jerks, I'm just saying that. They're quite evil creatures, but they're cute and cuddly. No, really though, there's like this podcast that follows a cat, like what a cat does, and it's pretty amazing what cats go and do, especially at nighttime. They're just like killers. They go out and kill stuff. That's what they do at night. All right. So let's just think about this question for a minute. So if there are two locations that both are at the same altitude and they have the same average wind speed, but the air temperature at one location is higher than the other, which one has a greater power potential?
Lower temperature,
Right.
denser air.
Okay, so the air is denser. And we could also go back to that equation, this equation, that if temperature is in the denominator, then a higher temperature is going to decrease the amount of available work that we can produce, or power that we can produce from this particular wind farm. Okay, so let's do another analysis where we look at two different possibilities and determine the average wind speed for each of those locations. So if there's a location where the average wind power density is 200 watts per meter squared, or one that's 400 watts per meter squared, we're going to look at that and see. And again, we're still looking at available power. This is not necessarily the amount of power that any one of these turbines can generate. Generally, their efficiencies are low, like around 30–40%. But if we're analyzing them and comparing them apples to apples to apples, then it's important to do these kind of analysis and calculations. Okay, so at location 1, we find that our W dot over A is equal to 200 watts per meter squared. So we want to find the average velocity at that location. And we know that W dot over A is equal to 1/2 rho times the average velocity cubed. Rho is given to us in this equation. So we can solve for this average velocity is equal to 2 times W dot over A divided by rho to the 1/3 power. So we look at that, we find that V average is equal to 6.97 meters per second. Do you think that the average velocity is going to be lower or higher at the other wind farm? What does your intuition tell you? Higher. Why?
The first one's poor, second one's good.
Okay. Okay, so it's a better choice, right? So again, 1/2 rho V bar cubed. We solve for V bar and we find that it's equal to 8.78 meters per second. So this is assuming that if these two locations have an identical or have different power densities, we can see what the velocities might be. But then we could take this 6.97 meters per second, we could say, okay, if this is what we're given, how can I increase our power density? Maybe I need to change something about my turbine to try to increase that. So, all right. So let's talk about efficiency, which is where we always end up when we're talking about electrical power generation, or any kind of work or power generation. We have to talk about the effectiveness of our system or our mechanism in actually harnessing that power that's available to them. Because although the wind is blowing at a certain speed, that doesn't mean that all of that kinetic energy from the wind is going to be transferred to our turbine. In fact, that's physically impossible for the wind speed on the other side of the turbine to be 0, which we'll talk about later. So there's a limit to it. And so when we're looking at our wind turbine efficiency, we look at how much shaft work we're able to get out of this turbine divided by the power that was available to us. So this is actually the shaft work per unit time. So this shaft work divided by the available power based on the wind speed and the area of our turbine. And then if we connect our turbine to a generator, there's also going to be some losses as we convert from mechanical energy to electrical energy. So our overall turbine efficiency is going to be this efficiency, or the mechanical efficiency of our turbine, multiplied by the efficiency of the generator, because efficiencies are products of one another. As you have more mechanisms in series, then you have to multiply the efficiencies together. So if we do that, we can see that our electrical power output over our available wind power generation is equal to our overall efficiency. Okay, so if your efficiency is given, then you're able to calculate your electrical power output based on a given available wind power generation conditions. So maybe the velocity is given, so you calculate this, what's available in that area, and then if you know your efficiency, you can determine how much electrical power output you would have for that particular system. So let's do an example of that. A wind turbine with a blade diameter of 25 meters is to be installed in a location where average wind velocity is 6 meters per second. If the overall efficiency of the turbine is 34%, we need to determine the average electrical power output, the amount of electricity produced from this turbine for annual operating hours of 8,000 hours, for unannual operating hours. And then the revenue generated if we sell that electricity at 9 cents per kilowatt hour, which is pretty cheap, right? So this is comparable to the prices from coal-fired electrical production. That actually solar power is a lot more expensive to implement, and therefore it costs a lot more, so the price is passed on to the consumer in a higher amount. Wind power is not as expensive, that it's on par with coal-fired power plants. However, the amount of electricity you're able to get out, as well as how many of these wind type turbines you can possibly set up in an area, is limited, which is why it's not more ubiquitous. That's why we haven't completely switched over to wind power. Okay, so our overall efficiency is equal to our electrical power divided by our available power due to the wind. So we can solve for our electrical power is equal to 0.34 times our available power. And how do we solve for our available power? What's the equation for that? Okay. M dot. We're not given M dot. We're given rho AV cubed. Okay, because M dot is rho AV. So it would be 1/2 M dot V squared, or 1/2 rho AV cubed. So we can plug the numbers in for that. 0.34 over 2 multiplied by 1.3 kilograms per meter cubed, multiplied by the area, which is pi times 25 meters squared over 4, multiplied by the velocity, which is 6 meters per second cubed. So we get a total power generation potential of 23432.17 kilograms times meters squared per second cubed. And a kilogram times a meter squared per second cubed is a kilowatt per kilogram times meter squared per second cubed. Oops, that's times, not divided. Kilograms times meter squared per second cubed. Okay, so we find that it's 23.43 kilowatts is the average electrical power output. Okay, so then if we operate this for 8,000 hours, we can say 23.43 kilowatts times 8,000 hours gives us 187,457 kilowatt hours. Then if we were charging 9 cents per kilowatt hour, then we can determine our profit generation or revenue generation. Kilowatt hours times 9 cents per kilowatt hour we find that we net or gross 16,871 per year. Okay, because it was 8,000 hours in a year. So 8,000 hours in a year, that's like 333 days, something like that. So they're assuming maybe there's, approximately 30-something days where, equivalent of 30-something days where the wind's not blowing or the turbine is out of service or out of commission. And you'll even see that sometimes if you're driving past these arrays, there'll be all these turbines spinning, and then one won't be spinning. Either it's has a problem, or that the brakes have automatically come on, or perhaps the vane is not turning correctly so that it's hitting the wind, that it may be stuck in some other way. Or if you look really closely, and I watched a video about this a couple days ago, it was kind of funny, that the people who do the repairs on these things are pretty much like climbing up ropes to get up there. There's not a ladder inside that pole. They have to tether on and climb up these towers like they were rock climbing, essentially, except they're like winching themselves up. So it's really cool and interesting. And so something in the video that it said, if you ever see a turbine that's stopped, look and see if you can see a person on it, because there might be somebody doing repairs. And they'll be like about this big compared to the size of the turbine, because those things are so huge. Okay, so from the energy balance, if we want to look at how much shaft power we're getting out of this turbine, we can look at the kinetic energy of the air flowing into the turbine, that if we just draw a control volume, it's an open system and it has imaginary boundaries because there isn't actually this tube-shaped thing over the turbine itself. But our velocity coming into the turbine is faster than our velocity leaving the turbine, and that's because some of that kinetic energy is converted to shaft work. So we can also express our turbine efficiency in terms of the shaft work, so that it's equal to this m dot v1 squared over 2. This is our work available, and then this is how much of that work potential was converted into shaft work. And if we want to combine those two equations together, we can solve for our velocity at the outlet in terms of our velocity at the inlet and the efficiency. That's an alternate way of comparing turbines and analyzing turbines, is looking at these outlet velocities and either calculating efficiencies or calculating outlet velocities based on efficiencies or predicted outlet velocities. So if you remember fluids or anything about Bernoulli's equation, you know that it's like the energy equation equivalent for flowing fluid, that the kinetic energy coming in plus whatever happens inside that turbine has to be balanced with the kinetic energy leaving. And that leads us to the discussion of the Betz limit, because in order for this turbine to be 100% efficient, the velocity at the outlet would have to be 0. But that's the only way that all of your kinetic energy at the inlet could be converted to shaft work, is if you had a 0 velocity. And the book goes through a pretty lengthy analysis of this to prove the Betz equation. We're just jumping right to the final conclusion, is that the maximum efficiency for any wind turbine is 0.5926. So about 59.3% is the maximum efficiency that any wind turbine can have. So not great, okay, similar to the Carnot efficiency for some of the power plants that we looked at based on thermal constraints. This is based on the constraints on wind velocity and being governed by the Bernoulli equation. So for wind turbines, that Betz limit is 0.5926, and if we plug that back into the previous equation, it means that our outlet velocity has to be greater than or equal to 0.638 of the inlet velocity. So if you have some design and you think, okay, I'm going to design this turbine, and the predicted outlet velocity is this, well, you could compare it to the Betz limit and see if you're designing a turbine that's not feasible, which is probably likely. So if we look at turbines that are in production, these are various types. You can look back to the original image several slides ago to see kind of how they correlate. But these are the efficiency curves for these various types of turbines based on wind speeds. And this is this is for the traditional main type that we see that's the curve for it. So you can see that at best, they're getting about 45% efficiency, which is not great, but it's also free wind power. So if we design our turbines well, and we try to maximize that available wind power and design them such that they're optimized for the wind speeds that are most prevalent in the area that we're considering putting these wind turbines in, then that's the best that we can do. So we compare it to the BETS limit rather than to 100%, similar to like we did with the Carnot efficiency. Yes?
This is kind of off topic, but this reminded me, when you were talking earlier about the horizontal ones not being being more efficient than the vertical ones, but due to size constraints, the vertical ones were used.
Sometimes.
Would it not be just as efficient to make the horizontal ones the exact same size you need? Or is the efficiency like not, what's that, two?
So part of the reason that a vertical one is chosen rather than a horizontal one is because with the horizontal, these blades are spinning out in different directions. Well, it's usually 3 blades or whatever. And so you have to have a certain clearance beyond those blades for safety.
Okay.
Whereas with a vertical shaft, you don't have to have nearly as much clearance.
Okay.
So in order to get maybe the same wind power out of it, with the horizontal design, you may have to have, this space allotted for it, whereas the turbine only takes up a smaller amount of space. But for the vertical shaft turbines, they don't need nearly as much clearance from the tips of the blades.
Okay.
That's one reason. But again, it's another one of those design problems where it depends on your wind speeds, it depends on your temperature, that there's so many constraints that go into it that every area where a wind farm is proposed for being put in, there's a lot of analysis that goes into it to determine the best size of wind turbine, the height of the towers, the airfoil design, just simply based on the conditions of that. So wind speed is one consideration, but there are a lot of other considerations as well.
Okay.
Okay, any other questions on that? All right, so let's do this final example. What time is it?
3 o'clock.
Okay. It's what?
Bullshit.
Okay, bye. Okay, last example. So in this one, we're going to look at wind speed variation. So we're saying, okay, the wind is varying between 16 feet per second and 24 feet per second. And it's in English units. So we have the same turbine in this location. It's 185 feet, so that's the diameter of the wingspan. And it's 30% efficient when the velocity is 16 meters per second, and it's 35% efficient when it's 24, this is supposed to be feet per second. And it's estimated the wind blows at 16 feet per second for 3,000 hours a year and 24 feet per second for 4,000 hours a year. And then we have a gearbox or generator efficiency. So we're trying to determine the total work or power potential of this site based on those considerations. And although the wind speed is varying between 16 and 24, they're saying, okay, for about 3,000 hours, we're going to call it 16. And for about 4,000 hours, we're going to call it 24. That it's a simplification of maybe a more complex actual scenario in this case. And we have to find the amount of electricity in kilowatt hours. So this is a good way to show unit conversion ratios from English units to SI units when we're dealing with all these crazy units. Okay, not crazy, you're fine. Okay, so let's look first at the 16 foot per second case. So we want to calculate our overall efficiency, which is equal to the turbine efficiency multiplied by the generator efficiency. So at 16 feet per second, it's 30% efficient, so it's equal to 30, or 0.30 times 0.93. So our overall efficiency when we're at 16 feet per second is 0.279. Then from there, we're going to look at our available power, which is equal to 1/2 times the density times the area times the velocity cubed, which is 1/2 times 0.075 pound mass per feet cubed for density. Pi times 185 feet squared over 4, and multiply by 16 feet per second cubed. So we find an available work of 4128806, and the units on that are pound mass feet squared per second cubed. Blech. Okay, so we can do two things. One, we can convert pound mass to pound force, because we're going to need that to convert to kilowatts. So 1 pound force is equal to 32.174 pound mass feet per second squared. And then now that we've converted our pound mass to pound force, we can also convert 1 kilowatt is equal to 737.56 pound force feet per second squared. So let's see if we did this right and our units go away. So pound mass, feet squared, and feet. There's another foot there. Cross that one out. Pound force goes away. Second squared with that one. Oh, this is not second squared, it's seconds. So we have kilowatts per second. No, seconds goes away. Seconds cubed, seconds squared, seconds. Seconds goes away. So we have 174.0 kilowatts. Okay, so this conversion factor, you could also use the following. 1 kilowatt is equal to, which I figured this one out, 23730.25 pound mass feet squared per seconds cubed. But that's a good one to know, to convert between kilowatts and whatever comes out of the kinetic energy equation for these. Okay, so let's do the second site. So we have 174 kilowatts. Actually, let's just continue this. But if we want to figure out how much actual power we're generating, it's equal to, so the actual is equal to the efficiency times the available. So if we multiply our efficiency times 174 kilowatts, so we use this 0.279, then we actually have 48.55 kilowatts. And then if we look at that, 48.55 kilowatts times 3,000 hours, then our kilowatt hours in this location, when we're operating at 16 feet per second, is 145,638 kilowatt hours. Okay, so that's how much we generate when we're operating at 16 feet per second. So we do the exact same thing to look at the example of 24 feet per second. So our available, let's see, our efficiency overall is equal to our turbine efficiency times our generator efficiency, which is equal to 0.35 times 0.93, which gives us 0.3255. So our available work, or available power, is equal to our 1/2 rho A V cubed. So our density doesn't change, it's just 1/2 times 0.075 pound mass per feet cubed. Our area doesn't change, it's still pi times 185 feet squared over 4, but our wind speed has changed. It's 24 feet per second cubed. Then we can multiply by our correction factor, which is 1 kilowatt is 23730.25 pound mass feet squared per second cubed. If you can't read that, just go look at the notes. So we find that our available power in kilowatts is 587.21. And then we're multiplying this by the efficiency, which is 0.3255, to get our work dot electrical, 191.1 kilowatts. And then we multiply that by 4,000 hours to find 764,400 kilowatt hours. So we add the two together, 764,000 plus 145,638 kilowatt hours. Find a total 910038 kilowatt hours. So that's the total electrical power generation at that site when we consider the efficiencies at the different wind speeds and how many hours the turbine will be in operation at those two different wind speeds as well. So again, these problems are not difficult. You have to be very careful about units, so make sure that as you're going through that you have the proper units. Don't just plug everything in and say you get kilowatts at the end, because you have to convert between meters squared per second squared and kilojoules per kilogram. So remember those conversion factors, and then this one on the other slide for converting between SI and English units. Because it is not uncommon that we measure things in feet and feet per second and English units, but all of our electrical power grid is measured in terms of kilowatts, SI units, right? So we don't have things usually given to us in horsepower or BTUs or any of those units that should naturally go with the English system. So it's weird. It's weird how we do that. All right, that's it for today. There are a lot of really interesting YouTube videos about these wind farms, and some that are less interesting, but feel free to look at those. If you have questions, send them my way.